Hello again, and welcome back to my computer vision channel. Today we'll be talking about MOTR, M-O-T-R, model for multiple object tracking using transformers, which is quite similar to another model called TrackFormer that I had a video about before. And today we'll be focusing on reading the source code. And here's the plan for today. So first, the setup, how to get the code, how to get the data. I actually written a small README file exactly on how to do that, but still I'm going to show you something so that you can have general understanding. Then we'll read the actual code, starting with the datasets. So how exactly we get the data, how we collect that into input sequence and pass it to the model, what sort of augmentations we use. Then we'll take a quick look at how the actual model inference is done. And here the model is really similar to just vanilla deformable data. And so it will just basically get predictions for one image. Then we'll take a look at the sequence input and what is called collective average loss, and how queries are being carried over from frame to frame, all that stuff during training. And finally, what happens during evaluation or during the actual work in real life when we don't have ground truth for the sequence that we see. So we have to change something to make the detection actually work. So let's start with the setup. First of all, we need to go to GitHub for MOTR. It's located at this megv research, and just get the code. And this repository has some instructions on how to get the data and actually install everything. Unfortunately, there's a lot of bugs and not everything works, and not everything is explained well. So for example, there's no clear instruction on how to actually convert the datasets. So I basically had to reverse engineer that. So to help everybody sort of repeat this process, I've just written my own README file that I've located in my blog repository. So I'll leave the link in the description, which basically explains everything you need to do. So we start with just fresh environment. We are going to need CUDA for this one because of the same deformable data model that keeps getting copied around from paper to paper. And it only has CUDA implementation, so it has no CPU implementation, it has no metal performance shader implementation for Apple, and so on. So you'd actually need an NVIDIA GPU for this one. And I tried to explain pretty well on how to actually download these datasets. So for mod challenge, that's pretty easy. You just click this get all data. For crowd human, you have to click on all of these links and download them. Nevertheless, I'm hoping that I explain it well, everything in detail. And so to test that actually works after all installations, we can just launch the actual training file and just validate that it actually starts to train and we see the first iteration. And indeed it is. So we see the first epoch, first iteration. So this means that it's working. So I'm going to interrupt that now. Another thing that I typically do is I just place a Jupyter notebook. In fact, you can see this Jupyter notebook in my repo as well, in the same folder with everything that I do. This is it. And so I'm going to just open this same Jupyter notebook in VS Code. This is just a notebook that I place in the root of the repository. So I have some functions which are just helper functions for plotting images, unnormalizing so that images that come from tensors look good, plotting boxes, and so on. And most of these code is just copied from the actual script of training. So if we go to main.py, thanks to the fact that we've installed the repository, thanks to the fact that this sandbox Jupyter notebook is located at the root of the repository, we can just go ahead and copy some of this code and execute it here, which allows us to basically interactively play with the same code and debug it and just see what happens. So just need Python environment. And that's it. And so what I do here is I basically take a sample image from the data set to see what it actually looks like, initialize the model, try to apply the model on this sample, get out the predictions, get the loss. I can press here to debug cell and actually read the source code as well, and just debug into it and step through the functions and so on and so forth. So this is my favorite setup, makes reading the code much easier, and it's pretty easy to set up. Next, let's take a look at the dataset code. So I'm coming back to my Jupyter notebook, just going to explain what's going on here. So first, we make sure that CUDA is available, because there's usually a lot of setup with NVIDIA drivers, CUDA itself, proper PyTorch with CUDA enabled, so it's always better to check before doing anything. Then, as I said before, there's typical functions to actually plot something in a proper format. Next, we have the arguments. So in the main script, we have command line arguments, which is not really convenient to work with in Jupyter Notebook, but we can just print out the actual object that is being created in place of args when we just launch the script, and then just place it right here. And so this object has args argparse.namespace type, and by initializing it like this, we can now pass it around in all the same code that we get from main.py that actually uses the args object, like this one, for example, and it will still work. So next, I just keep copying stuff from the main function. So here we have some initialization, device, random seeds, and then the data set. And so when we initialize the data set, we can see that it registers some videos. So the first one is from CrowdHuman dataset, and the rest are from Mod17. So let's actually take a look at them. So here's the CrowdHuman. Let's switch it to gallery. CrowdHuman is an object detection dataset. So it has independent images with people, not really connected to each other, which means that we basically only have one image in a frame. Despite that, we basically parse it as a one giant sequence of frames, despite the fact that they're not really connected, and we'll see how we deal with that in code in a second. And this is Mod17. So we go to train. There's a bunch of sequences here, and let's look at the first one, for example. Also switch to gallery. Now in Mod17, we actually have videos. So if we just quickly iterate through the images, we can see that now they are connected to each other, and they actually create this sequence of frames that makes it a video. So as promised, we can just go to definition and try to read what's going on here. So again, there's a bunch of options here. I'm not sure which one is actually getting called. So to find that out, what I can do is just click here, debug cell, and just see what happens. And so I'm iterating forward. And I can see that dataset file is E2E joined, and this is what we're building. And so when building, we have this transforms, which we'll look at in a second when we actually get the first image. And then we have this mod detection dataset. So during initialization, it's just basically going to parse various files here. So let's iterate here, see what happens. So the data.txt path here is datasets data path joint.train. So you can actually open this file and see what is it about. So you can see here that the first bunch of images comes from CrowdHuman, and then and CrowdHuman validate for some reason. I'm not sure why is it coming from just validate. And then toward the second half, it's coming from Mod17. And so when we actually parse the data, we just basically open this annotation file with all the images that we need. Then we just read all of them independently and basically create actual video sequences out of that. And we can take a look at how that looks like by just grabbing an example from the dataset. So example number 0 is going to come from CrowdHuman, as we've seen. And it's basically a dictionary with an image tensor, and some labels. So for example, with labels, we have ground truth instances, which are the actual classes. So all of them are zeros because 0 stands for a person. We also have more stuff that is actually useful for object detection and object tracking. So we have bounding boxes for coordinates. We have object IDs. So for CrowdHuman images that are independent, we're just going to generate them from 0 to number of objects. For mod 17 objects, we will actually get the ground truth object IDs that are persistent frame to frame. And we can actually plot it and see how it looks like. So this is a CrowdHuman dataset example. Another interesting thing we can do right now is we can just grab the same image again, and you just notice that the actual numbers are different now, right? And if we plot it again, but in a separate cell, we'll see that the image is slightly different now. So these are the augmentations that are being used. So augmentations basically reinitialize every time we actually fetch something from the data set. And so if we just keep repeating this, keep plotting the images, we will notice that it basically gets flipped left to right sometimes. Sometimes it will get like a slight shift. Sometimes we will get like we've just seen, like this white padding that basically obstructs half of the picture. Here I think it got zoomed in a little bit. So these are the augmentations used here. They're not really that intense as we might have seen in other detectors, but still they basically make the training data more variable. And let's also grab some examples towards the end. So like second half, this one should come from MOTR. Now we see that we have much more objects. And here's how the example looks like. So this is from MOTR, and we can validate that by taking the next image and plotting it again and validate that this is actually the same sequence, right? But it does get slightly different augmentations from frame to frame. So next thing I wanted to show is the way we get the longest sequence from the dataset. So let's go to main.py just for a little bit. First, like to actually understand what's going on here, let's take a quick look. So we started somewhere here in the main function. And we can see here that we do build model to get the actual model and loss the data set. Then on top of the data set, we also have sampler and data loader, which basically allows us to load the actual batches of examples from the data set, randomly sampled. Optimizers, distributed mode, and so on and so forth. And then this one is only if we continue training, and then the actual train loop. And so for every epoch, we're going to do this epoch steps. Most of the actual logic is hidden inside this train function, train one epoch, and then evaluation. And somewhere here in the end, we have this step epoch function. So let's just go to that one, and we can see that we track epoch in the dataset. And we need this because we basically start training with the sequence length of 2, and as we progress, as we train for more and more epochs, we actually increase this sequence length. And so we can check here first that when we just started, the length of images that we get in one example from the dataset is just 2. And we can say something like, let's set epoch to 150. And then try to get example out of the dataset and see how many images we get there. Now we get 5, right? So this is the technique used in training. This is my slide for it and from the previous video about the actual algorithm. And this is another difference of MOTR to transformer. So in transformer, we only get 2 images in a sequence, which means that in cases like this, like when we start where 2 objects are quite far apart, then they come closer together. So even though this particular situation where we have 2 objects really close, it's really easy to confuse them for the model. So this is probably the most dangerous case for object tracking. And you can see this is exactly what happened. The model sort of confused itself, right? But then the actual loss, which usually relies on either mean squared error, distance, or intersection over union, it is really small because the objects are close together. So the loss is small exactly because the objects are close. So we don't really get much use out of these examples, which is quite unfortunate. And this is quite well fixed with just longer sequence. So if we have more images from the same video, we'd see that the objects were far apart, then they came close together, and then they came far apart again. And so in the last frame here, we can see that the model did confuse them, and now the loss that it will get is actually quite big, which should be enough for the model to train properly. And let's actually see what happens when we try to fetch an example from the dataset. So we were in this MOT detection, which is basically the class responsible for fetching the data. We've read this init function that initializes the data path. We can see one function named getItem. So this is Python syntax. If you create a function called getItem with 2 underscores, you basically create your own method for getting something out of a collection using square brackets. So let's just put a breakpoint here, and then I'll just press debug cell. So I've stopped here. I can validate that the IDX that I've got is 0. So first we get this get sample range function, which is defined here. We have some different versions of sampling. And to demonstrate what it does, we can just execute it and see what the result is. And so what basically happened here is we got 0 index as an input. So we are being asked for image number 0 of the entire data set. And then we say, okay, well, to generate the sequence for that image, we're going to take images 0 to 33 with the stride 8. So like 0, 8, 16, and so on. And then we sample them here, over here. So pre-continuous frames is going to get just range over that, so we can actually execute that and see what indices we get. So we get 0, 8, 16, 24, 32. And then we basically fetch single frames. So let's see what the method is. So I continue here. Now, press single frame should look a lot like just a normal object detection data set. So we have these image files, which is something that we've parsed when we initialized the data set, and we basically remembered where each image is. So we open the actual image. We have labels for the same image as well. we say the information like which dataset this image came from. This is where we iterate over the actual ground truth. So boxes, labels, just continue to here and read that a little bit. So we have boxes, which are just 4 coordinates per object with the actual coordinates of the bounding box. Area is something, I guess, needed for segmentation only. I'm not sure what is crowd is not used in current training. Labels are typically zeros because we mainly deal with persons. Object IDs are actual track IDs, which is just generated for crowd human and read from the actually annotations for MOTR. So let's continue. So one interesting thing here is that like we're supposed to get an image, like 5 images from the same sequence, right? For now, like that probably will happen for MOTR dataset, for like second half of the dataset where images actually come in order and they come from the same video. Although even then, so far we haven't really looked at the end of the video, so we didn't know where the video ends, and so we might occasionally just sample the frame from the next video, which is not good. And then for crowd human, all of these are going to be from like basically different single images, and we can just validate that looking at shapes. So the first one is 800 by 600, second one is slightly different, and so on. And what will happen in this case is we will have these transforms as well, which will deal with that, and we'll see how exactly in a bit. So we've defined these dataset to transform when we initialize the dataset. So this build E to E joint, this is where it builds the transforms. So let's go here. And you can see here that we have 4 versions: MOT for training test and crowd human for training test. So let's look at crowd human first. So we have this 2 tensor, normalize, random horizontal flip, random shift, resize, crop, resize. So yeah, these sound like typical augmentations for working with images. So it took me a while to find the one that's actually responsible for fixing our video sequence, and I think it was this one, fixed MOT random shift. So I can just put the breakpoint here, and since I'm already in the process of fetching an image, so this transform was built when we built the dataset, and it's now applied every time we fetch an image. And you can see here that now images is a list of length 5. They're still not transformed to tensors, and we can see that they all are slightly different sizes. So what basically happens here is we're going to do some random shift. Like we're going to basically take the first image, right? Because we start with I of 1, and save the first image as this previous image, and then we basically repeat that on each step. And what we do to actually get slightly different images in a sequence is we do this random shift. It just basically shifts all the pixels somewhere. So this is a slide image augmentation to make the images in sequence actually different. But thanks to the fact that we always refer to the same image in the code, we can see now that they are of the same shape now, right? So we started with images 800 by 600, 960 by 720, and so on. And we only are going to use the actual first one, 800 by 600, slightly modifying it to actually look different for different elements in the sequence. So this is a bit weird, at least because training takes quite some time and it's quite expensive, and in many cases it's actually I/O bound. So the faster you load images from the disk, the faster you're going to train. And here we're basically making that 5 times harder because we're loading 5 different images from the disk and then just basically just throw away 4 of them, which is weird. Not the only weird thing about this model. So this is for CrowdHuman. And now for MOTR, for the actual video sequences, as I told you, mostly they will come from the same sequence, but then there's this moment of end of video where, if you're not careful, you're actually going to take some images in sequence from one video and some from another. And at this point, your ground truth for tracking basically breaks down because like all the ground truth objects change from frame to frame. And this is actually what happens here. So I found that example, right? Example number 4960. And we can should plot 2 images from this example and see that they indeed come from different video sequences. So the first one looks like this, some people on a square, and then the second one looks like this, some people on a road with a car. So again, I guess just the authors were a bit too lazy to handle that, but still, this happens quite rarely because we have a lot of images in a sequence, and so only maybe 0.0%, 0.1% of cases will get this end of video thing. So it doesn't really hurt the training so much. So next, let's just finish reading the dataset. So we've read the actual dataset, which is usually responsible for fetching just one example. And in our case, that one example actually is going to have up to 5 images. Then we also have a sampler, which basically now generates random indices for every step during training. And it's also dealing with batches. So let's see what the batch size is. Batch size is just 1, so it's not really that relevant for us, but still it is possible to make a bigger batch size. To deal with that, there is also this collate function, because we actually have batch size more than 1. We're going to have images with different sizes in a batch, and to deal with that, we need to pad a smaller one of them so that they all are in the same dimension, because this is how tensors like to work, including, and we also need to remember which part of the image is just padding and which is not, so that we apply the transformer properly. And that's it. So now next we have this data loader, where data loader is basically an iterable over which you can just iterate and get randomly sampled batches of examples. This is what you'll actually train on. But the images are pretty much the same, so all the transformations already happened. And let's just validate that by plotting one more image. Now from this sample. So sample. Yep, this is still MOTR dataset. So once we have that, once we have our sample, which is now a batch, we can initialize the model. There's also this datadict to CUDA method, which basically allows us to place a dictionary on CUDA as well, or on a necessary device. And then once we have sample and model, what we can do is just call the model, right? So this is really important because it allows you to just apply the model, debug it, play with it interactively. So this is what we are going to do next. So we are ready to look at the actual model code during training, and we start with just single frame inference. So first, we have our sample, we have applied the model, and we got out the predictions. Let's take a quick look at them. So I'm going to just print out everything that we have there. So we have pred logits, pred boxes, and losses dict. So loss calculation is going to be part of the model call itself. So we'll take a look at that. And then pred logits are basically probability predictions for each class. And then pred boxes are the actual 4 numbers per prediction for the actual bounding box coordinates. And so we can print out like the shape of that. So pred logits is a list, and in our case it will have the length of 5 because we have 5 images in a sequence. So basically the model returns predictions for every element in the sequence, and then the shape of that is 1 by 300 by 1. So basically we get out 300 predictions for every frame, and so we'll have 300 probability predictions for that specific class being a person, and then 300 by 4 numbers per frame for the actual bounding box predictions for every potential object. And the actual matching to ground truth objects, the actual loss calculation is also part of this model call. And to take a look at that, we need to put the breakpoint first. And to find it, I'm going to this build model, which is MOTR model. The code itself is quite similar to just the vanilla data and every other model that came based on that one. You can see that the model itself is a class called MOTR, which inherits from an NN module. So this is the actual neural network, PyTorch NN module that is doing all the work. And so the actual call to the model is always forwarded to this forward method first. So I'm going to put the breakpoint here and just see what happens. And indeed, here I am. And so data is everything that I am passing in, which includes like everything that we've got out of the data loader, basically, which includes images and basically ground truth instances. And the call itself is quite short, so you can see like, 50 lines of code here. So here, what it is doing is it starts with initializing track instances, which are basically these track queries that get carried over and updated from frame to frame that contains necessary information for tracking objects. And so that will include, as we'll see, the actual query embeddings and quite a bit more stuff, honestly. So let's just take a look at that. So I'm initializing, I'm looking at it here. So we can see that track instances have quite a lot of stuff there. So some of that is mainly filled with zeros, but not everything, right? So like this ref points here, for example, is not filled with zeros. So is this query position, and then some of them are initially filled with zeros. Or just -1s. So first of all, two main things that is actually used in model inference call are going to be this ref points and query position. So query pos is query embedding. It's called query pos because this query embedding sort of acts as a positional embedding input for the decoder. But this is basically like the actual embedding of an object that we track. And we can see that it is initialized with self.queryEmbedding.wait. And so the type of this self.queryEmbedding is torch and then sparse embedding, which is a fancy way of saying that it's just a trainable parameter, static trainable parameter, meaning that it's not really dependent on the image itself. And you can see here that the shape of that is 300 by 512. So for every of the 300 query inputs, we're going to have this 512 long embedding. And then reference points basically take the same self-query embedding and then apply self.transformer.reference points, which is just a linear layer to convert that to the actual reference points. So what are reference points and what are query embeddings? So query embeddings come from data itself. So in the original data, we have this decoder input, which always comes from this statically initialized trainable parameters. And then for MOTR, when we actually track some objects, apart from some statically initialized queries that in the paper are called detect queries, we're also going to have queries that get carried over from model outputs of the previous frames. So these are the query embeddings, or query POS as they're called in the code. And reference points come from deformable data. So this is an image from deformable data paper. So a quick reminder, deformable data and deformable attention is attention modification that allows us to look only at specific points, specific pixels for this pairwise interaction instead of just computing everything. So basically, like for this example image of some football players, we'll have deformable attention in the encoder and the decoder as well. And so instead of just computing all the pairwise interactions for attention between all the potential pairs of pixels, what we instead do is we take what is called a reference point and then compute the fixed number of points based on offsets. So we have a layer that just predicts the offsets, just 3 numbers or 4 numbers that depend on the value within this pixel. And then we just sample attention from these points only. And so reference points are different for encoder and decoder. So for encoder, it is pretty obvious because we take interaction between a pixel within the image and a pixel within the image. And so in this case, like the logical choice for reference points for one of the pixels is just that position of that pixel itself on the second image, right? So it is multi-scale, as we can see. So we start with less processed by high resolution image, and then basically process it, reducing the spatial resolution, but increasing the embedding dimension. And so we will have like pixels from the smaller frame tending to pixels in the larger frame. And to get this initial reference point, we just basically project this part of the image here to find out its coordinate. Now, that is not how it might happen in decoder, because in decoder, we're going to have interactions between object queries and image pixels. And so object queries by themselves don't really have that logical location within the image. And so to find out reference points for them, in the original deformable data model, we just took the query and then just projected it down to some point within the image using just one linear layer, which basically makes it trainable. So the query is free to decide for itself where it should look at. And then from there, we actually compute the offsets and find out which actual pixels are we going to attend to. And so as we'll see later in the code, so for just when we just start processing the sequence, we also take this static object queries, apply this reference points layer to arrive at this point within the picture from where we start the offsets. And then for later frames within the sequence, we are going to take the query output of the model and also use that one to find out the new reference points. So we basically have like object representation, and we use it to track objects, and we use it for query embedding as well as for reference points in the model itself. And you can see here that the process is really similar to deformable data. So we also take self-query embedding and then apply this reference points linear layer to that to get reference points. And so reference points are just 2 coordinates, x and y, for each of the 300 queries. And the rest of the stuff is just default initialized. So some of that will represent the actual track IDs of the objects and so on. That is what we'll look at in the next part. And so reading forward this forward method, we'll see that here we iterate over frames. Then we have this function, which is applied using this checkpointing mechanism. But the function itself is basically converted this frame to nested tensor and then calls this self forward single image, which basically takes an image and applies the model. And then after that, we also have this post-process single image that take the result of this model call, takes the track instances, which also contain information about ground truth objects, and does this post-processing, which basically deals with matching the predictions with the actual ground truth objects, carrying them over from frame to frame, adding false positives, false negatives, calculating the loss, and so on. And so the actual forward call is going to happen here. So let's just go here and just continue. So this code is already quite familiar to those who read the code for data or deformable data. So let's print out like what is the input. We have samples, which is a nested tensor. And we need a nested tensor because we might have batching, and batch might have images that are padded to the same length, and nested tensor basically takes care of that. So it tracks which parts of the image are padding and not. So it has this mask, which is not really relevant for us because we only have batch size of 1. So you can see that the actual tensors here have the batch size of 1 and then 3 colors. And these are the actual image dimensions. So the very first thing we do here is apply a backbone. Let's see what it is, by the way. So it's a join of a position embedding, which is also part of backbone in some sense. And then this one has batch norm, max pole, bottleneck, conf2d, frozen batch norm. That sounds a lot like ResNet, to be honest. And so the output of this is going to be a list, as far as I remember, with 3 images. So the very first one has embedding dimension of 512, and then the largest spatial dimension. Then the second one has slightly bigger embedding dimension, and then smaller spatial dimension, and then the last one has the biggest embedding dimension, and it's even smaller in resolution. So this is us creating this multi-scale input. So we started with just a raw image, which is really big and only 3 numbers per pixel. And then we processed it down to smaller resolution, but then a lot of information stored in each pixel. And positional embedding is pretty much the same, but the actual value stored in each pixel will only depend on position of that pixel. And this is the sine-cosine embedding. So what we do next is we are going to iterate over these sources. And first of all, we'll apply this input projection. And the input projection is a list of modules, which typically projects everything down to 256 embedding dimension. So for example, the very first scale, as we've seen, has embedding size of 512, and we project it down. The next one is even bigger, but we project it down to the same size, and the next one is even bigger. Apart from that, we actually want 4 feature layers here. So we want 4 scales, but we only got 3 out of the backbone. So what we do is we basically apply the same projection convolution layer, but now with a kernel size of 3 and stride of 2, to basically shrink down our smallest image even further and get the 4th scale with even more, which is even more processed with even smaller resolution. So I'm just going to go forward here and just demonstrate that. So now length of sources is 4, and the final scale is even smaller. So it's 12 by 14 pixels. Really, really, really small image. So then we are going to basically pass that through the transformer. We'll read that in a bit. The transformer itself is actually really similar to Datar. It's actually pretty much equal to deformable Datar. Let's just take a look at the remainder of the code now and like what are going to be the outputs. So one difference to TrackFormer that we can see here is that TrackFormer actually received both images, so this image and previous image, as part of the transformer call, which allowed it to do stuff like do the decoder with attention to this image and the previous image. So in a way, when creating, like when detecting, when tracking the objects on the next frame, it could actually refer to the previous frame as well to do the tracking, apart from the queries that came from that frame. We don't do that here. So here, what we receive from the next frame, all of that is contained in the query embedding and the reference points. We're not actually looking at the previous image. So the output of this call is this HS object, which has the length of 6 by 1 by 300 by 256. We have 6 layers in the model. And so typical for data-like models is that we actually get output of every layer out of the transformer itself, and we're actually going to use that in the loss. So we're going to compute the loss for each of the outputs of every of the 6 layers. And what we do afterwards is we keep track of the reference points because we are going to pass them from frame to frame. We apply this classification embedding, which is just a linear layer that projects 256 numbers down to 1, because we are only interested in one class here, person. Bounding box embedding, which is slightly more complicated. So instead of just one layer per transformer layer, we have now 2 linear layers. So one is just doing projection to the same size, and then we project it down to 4. Nevertheless, this is what is called MLP, multi-layer perceptron. It's not really that different from just the linear layer, and the output is 4 numbers per every query. And we're going to save all of that and actually pass that out. So let's continue here and just print what we actually get as an output. So out keys. We get pred logits, pred boxes, which are actual outputs of the model, like what are we detecting. We get auxiliary outputs and HS, which basically correspond to like intermediate layer outputs that we save and pass around to compute loss, and the actual reference points. So reference points we pass out to basically keep track of them because we are going to pass them from frame to frame. You can notice here that we don't predict track IDs. Instead, track IDs are implicit in the position of the query and the corresponding output to that one, as well as the matching that will happen afterwards. We also don't create this, what was called time aggregation network or query interaction module, which basically takes the detected objects from the current frame, passes them through an extra attention layer, and then creates query inputs for the next frame. So this is going to be the part of post-processing. So another interesting detail that I forgot to mention is the output for ref points. So you can see that ref points all is an array concatenation of initial references and inter references that got returned by transformer, and the length of this array is 7. And here we take element with index 5 as an output, which roughly corresponds to second to last layer instead of last layer as it's supposed to be. I guess that's a bug, not a big one. Basically, to carry over reference points from frame to frame, we don't take model output, but take second to last layer instead of the output. A bit weird, but okay. And then, as promised, let's restart the thing and read the transformer code. So again, the initialization of transformer is happening in the same file, MOTR.py build deformable transformer, which returns this deformable transformer module. So this one is actually exactly the same as the original deformable data model, but let's read through that quickly anyway. So we can see that it inherits from nn.module. So I'm just scrolling down to forward method, put a breakpoint here, and then restart my debugging. And here I am. So again, verifying what sort of shapes we got. So we get 4 levels or scales as an input. The same for masks, same for positional embeddings. We also get these query embeddings, which are either initialized randomly for the first frame or actually passed around from frame to frame with slightly more complicated time aggregation network for second frame and afterwards. So the first thing we do is just we iterate over all our levels, source, mask, positional embedding, and just flatten them all down. And slightly interesting detail from deformable data here is that we also have level embed. So again, a reminder, if we have multi-scale input, the positional embed is going to tell us like where within the image is this pixel located, because we're going to flatten everything out and pass through the decoder, and thus we'll lose all the positional information. But we also pass in all those scales sort of flattened and concatenated together. So to keep the information about which level the pixel was in, we also have this level embedding. And the type of that is parameter. Shape of that is 4 by 256. So we have 4 levels, and we get just trainable, statically initialized vector for each level embedding. So we append that, we add that to positional embedding, then flatten everything out. And if I just continue to here, what I'm going to see is that now my source that will be passed around further is this one giant sequence of tokens with 23k elements in this case, which corresponds to basically all the 4 scales that we had flattened and concatenated together. But it's not that computationally expensive to process that, because we use deformable attention, which is not going to trigger quadratic time complexity. Instead, it's linear. It's only basically looking at 4 pixels for each pixel interaction. So then we have this self.encoder, which can be seen as just taking this flattened input, passing that through self-attention, and then the output of that is exactly the same shape. So I'm going to quickly read the code for that. So we have encoder and encoder layer. So encoder itself just basically iterates over all the layers, 6 of them typically. Here we have logic for reference points again, but now since we're talking about encoder, we're talking about image-to-image interaction, it's just computed knowing the actual shapes of the image. And then we apply the encoder layer 6 times. And so if I scroll down to encoder layer, again, it's pretty straightforward. Self-attention with pose embedding. Pose embedding is just going to add the input tensor and position embedding tensor. Then this plus here stands for residual connection, normalization, feed-forward network. Again, all this typical stuff for transformer. The only actually interesting thing here is that as self-attention, we are using this custom MS deformable attention module that does not have quadratic complexity. It has linear time complexity. That, again, I'll just refer you to deformable data model. So now let's just iterate towards the beginning of this memory, this encoder computation. So input to the encoder is going to be this flattened source with 23K tokens. And the output has the same shape. So 23K by 156. So next we have the logic of basically calling the decoder. Self.toStage is false because we're not using toStage here. So then, yeah, so one detail that I forgot to mention here is that, again, contrary to what happens in TrackFormer, that might pass in two images to the forward call, here we always only deal with one image, the current frame, and all the information that comes from previous frame is passed in through these query embeddings and reference points. So you might have noticed that query embedding shape is 300 by 512, which is twice the embedding size of the rest of our network. And here is the explanation. So usually when talking about decoders or encoders for that matter, we have sort of one input and another input, and one of them is typically called just the input, and the second one is called positional encoding. So for encoder, the input is the image with the actual pixels, and the second input is positional encoding. For the decoder, in original deformable data, as far as I remember, one of the inputs for the first layer is just 0, and another one is this query embedding. And then for the second layer and the layer afterwards, the first input is going to be the output of the previous layer, and the second input is going to be, again, this positional encoding. So here we do it slightly differently. So instead of taking this target, which stands for the first input, instead of taking it as zeros, we actually just take the query embedding, the twice the dimension length of that, and just split it in half. So now I have 256 for query embedding and 256 for target. Not a big difference. And then I'm calling the decoder. Again, decoder here is exactly the same as in deformable data. Let's quickly read it anyway. So we have deformable transformer decoder layer. Mostly the decoder itself, again, is iterating over all the 6 layers, although we see some reference point stuff happening here. And then when we call the layer, again, we have quite a bit more stuff, to be honest. So if I scroll down to forward, and I'll put my breakpoint here and continue. So we have 2 function calls here, either forward self cross or cross self, depending on whether we want to do self attention, query to query first or after the cross attention. Let's see which ones will happen. Okay, so we're doing the first one, self cross. Again, it's rather short, quite typical for transformer layers. So we have forward self attention, we have cross attention. Let's again break here, see what's happening. So we have target, query position, which query embeddings basically reference points, source, which basically comes from the image, and then a bunch of spatial shapes. So we have forward self attention, which is itself a function that does self attention, residual connection, dropout, normalization. Then we do cross attention. And if we look at how all of that is initialized, So for self-attention, we use just typical pytorch.nn.multi-head-attention, which is the classical quadratic complexity full pairwise attention. For cross-attention, we are using deformable attention again. And this is because basically we only have 300 queries, so it's not that hard to compute like 300 squared interactions, but we have 23K pixels in the image, so where we cannot afford to do full pairwise attention between queries and that, and so we use deformable attention. We can see that cross attention gets these reference points as basically part of the deformable attention thingy. Then again, we do residual, normalization, and forward function. So let me quickly return to the one layer up to the decoder. So we were calling this layer, so let me just continue here. So at this point, I basically applied one decoder layer, which basically now takes input queries, which are going to become detected object representations. So we start with just some either static, basically anchors that we train that do not depend on the image, or with queries that got passed in from the previous frame. And then as a side input for decoder for cross attention, we have the image. And so we'll have a bunch of query-to-query interactions and query-to-image interactions for these object representations, acting as experts to interact with each other and exchange information, to look at the actual image and modify their modify their state to actually detect some objects. And so we'll have layer after layer after layer of that, 6 layers in total, having like the final query embedding representation as an output. And this final query embedding representation will have the same shape as input, but now if we apply bounding box embedding and class embedding to that, we get out the actual model predictions. So another piece of code here that we see is how we deal with reference points. So the very first set of reference points, as you remember, was either initialized from query embedding or passed in from the previous frame. So this is like either just static, again, anchor point that just says, okay, on this image, this query is going to look here, or it was passed in from the previous frame, at which point, as we'll now see, it basically represents the coordinates of the object detected on the last frame. And this is actually the piece of code that is responsible for that. So here we just have applied a new layer. And now we're saying that, okay, well, I need updated reference points. So first set of reference points did not actually depend on the image. But now I had one layer of interactions of queries to each other and to the image. Queries themselves updated their state to now more closely represent some objects that are there on the picture. And then we use that, so we use this output. We apply bounding box embedding to that to get basically bounding box predictions for all the objects. And then we use those bounding box predictions, and bounding box predictions are x and y coordinates and height and width of the bounding box. And we can obviously use the x and y coordinates as just basically the location of the object. And this is what is happening here. So new reference points are initialized as the first two coordinates, x and y, of this predicted bounding box. So what this is actually predicting are not the coordinates of the bounding box itself, but rather the change, the shift in the bounding box that we try to do in the layer. So basically the layer is not predicting like absolute coordinates. The layer instead takes in some sort of anchor and then modifies the coordinates of the anchor to more closely match the object. That's why we also have this sum here with the previous reference points. Which kind of makes sense, right? So reference points that are used as a center of attention in deformable attention, we say that, okay, well, we seem to detect an object here, so let's just use that as a center of our attention. Makes sense. And we're also going to basically append all the intermediate outputs to this intermediate object. because we're going to feed in all of that into loss. So again, to demonstrate all of that on the screenshot from the paper, so we are here in the decoder where we have object queries interacting with each other and with the image. And so we will have all the intermediate outputs coming out of the network and being connected to the loss. So basically, we'll take embedding outputs from the first decoder layer, project that down to bounding box coordinates and class predictions, match to ground truth objects, and compute the loss. And we'll also sort of use the same object detections basically as updated reference points in the next layer and the next layer and so on. So basically, layer by layer, the network basically improves its detection, improves understanding of where exactly the objects are, and it then uses that improved understanding to refocus attention in the formable data case to that specific spot. And so this is about it. So let's go one layer up. So this was the formable transformer decoder. One layer up is just the transformer. So you can see that, yeah, like decoder call is one of the last calls, and then we basically return the output, which concludes the forward pass for the model. And we can just see what the shapes are of this. So as the main output, this HS, we basically have all the 6 layers outputs, 300 queries, and for each query we have an embedding of length 256. And so this is the transformer output. And if we go one level up to the MOTR detection model, transformer calls will return from here. And then we'll basically iterate over all the layer outputs, all the 6 of them, and we'll apply the classification embedding and bounding box embedding, and then just concatenate it all together and return. So now if I continue to here, I'll see that my predlogits shape is 300 by 1, because I only have one class, and then boxes 300 by 4. And then I also have these AUX outputs with all the intermediate stuff as well. So like main output of the model now for the single frame would be the classification, prediction, probability, and bounding box predictions. So that was it regarding like model inference for one image. Now let's take a look at what happens when we have a sequence input and what's collective average loss and time aggregation network. So if you recall, we had this forward single image call as part of this cycle in just the forward method. So, and let's say we don't use checkpointing, so then we basically just get this frame result from here. So we're still in the forward call for the overall model that receives up to 5 images in a sequence. Then after getting this single image prediction, and we do that in a loop, so we'll do that 5 times, we post-process that result, and we have the frame result with the actual predictions of the model, as well as track instances with a bunch of information such as query embeddings, reference points, as well as a ton of other stuff like ground truth, track IDs and object IDs and so on. So far, we've only seen that the use of query embeddings and reference points. And so this post-process single image will use the rest of the stuff. And then after that, we basically repeat the cycle. So yeah, just post-process, and so it's an iterative process. So the post-process result of the current frame will be then fed into this next frame prediction. So let's read what is it about. So we have this post-process single image. We take out the actual predictions, tracking scores as predlogits. Then we have this match for single frame call. So let's just continue to here. So we have self.criterion, which is a clip matcher, and we call this match for single frame function. So clip matcher is initialized in the same file, motor.py, down below, as well as transformer and motor model itself. Here it is, the criterion. and we have this match for single frame method. So let me just break somewhere here, continue, and see what is happening. So at this point, everything the matcher receives is inside this output. And you can see that it had the actual pred logits, pred boxes, some were there as well as the role model outputs, as well as the actual ground truth objects that we get from ground truth data and so on. And so then what this matcher does basically is it takes model outputs, and the model at this point is not really aware of any ground truth. So it just tries to detect what is there in the picture and matches that with the actual ground truth objects. And so we can see that happening. So we have some useful comments here. So step one is just inherit and update previous tracks. So we're looking at track instances, like those objects that we already tracked in the previous iterations. Let me continue to here. For now, we're just looking at the first one. So it's not going to happen. So you can see that in our case, track instances object IDs are all -1s because no objects have matched so far. But basically, this huge chunk of code is for carrying over objects from the previous frame. Then we select and match slots. So, and just see what slots we need to match with new model outputs. And in our case, that's going to be just all the objects. So unmatched track indices shape is 300. Then we have this matching logic. So it's hidden here, this match for single decoder layer, which is called down here, which takes unmatched outputs. Let's again continue to here. So unmatched outputs are going to be the dict with 300 pred logits and 300 pred boxes. And we have this self.matcher. So self.matcher is a Hungarian matcher. So we'll not take a close look into it, but basically this is the same Hungarian matcher that is used in Datar, in the loss for Datar, and so on and so forth. So basically what it does is it takes the actual model outputs, it takes ground truth objects, and try to match them together, maximizing some sort of score. And actually, yeah, let's go ahead and read that one. So we have Hungarian matcher somewhere, which is built over here. Hungarian matcher has the forward method. And let's just continue. So let's see what sort of input it gets. So it has outputs, basically predictions of the model, logits and boxes. It has targets, the actual ground truth objects, and you can see here that it has 25 instances, each with boxes, all that we need to actually match them. We are using focal loss, and so here we have some computation that basically computes the classification loss. So it's something like negative log likelihood or cross entropy, but with extra weighting to basically give more weight to hard examples. Then we have bounding box loss, generalized intersection over union loss. So these are basically typical for Datar, for detection loss. So we have ground truth object, we have our prediction for the model, and we compute the loss between the two of them as classification loss. So how close was the model probability prediction to the ground truth, which is quite weird for one class case, but still. We compute just the mean squared error between the 4 coordinates of the bounding box of these two objects and intersection of them. All of that is sort of summed up in this one giant loss, which at this point is computed over all the pairs. So if we just continue to here, we'll see that this C matrix has a shape of 300 by 25. So for each of the 25 ground truth objects, we compute the loss to each of the 300 model predictions. And then what we do is we call this linear sum assignment method, which you can encounter quite frequently in object tracking. So this one comes from scipy.optimize. And what it basically does now is it takes this full pairwise loss matrix for every possible combination of matching, and it computes such combination that one object from the model output is matched to exactly one object in the ground truth, not more. And it computes the optimal matching that will basically return how the matching should be done. The indices here will look like this. So length of that is 2, oh, sorry, just 1. So yeah, indices basically say, okay, which query outputs from the model matched to the specified objects. And you can see that query output number 2, number 20, number 45, number 50 matched to object number 11, 23, 18, and so on and so forth. In total, 25 of them. So some of model outputs were not matched to anything. So now returning back here to my match for single frame. So we've computed the matching. So now we got some new model predictions that we got from the current frame. We match that to ground truth that we've seen for the same frame. And we save that to our detector state, basically, to the object IDs and matched ground truth indices for these objects. Another interesting step is we calculate IOU, intersection over union. It will be used later for filtering, as we'll see, and also calculate the loss. So we iterate our losses that we have, like cross entropy for classification, and mean squared error, and generalized IOU for bounding box loss, and then just save all of that into our self.losses dict. So we repeat the same loss calculation process for all the auxiliary outputs, so all the intermediate layer predictions, and then we return. So this was the match for single frame method. We can see it happening in this post-process. And then second interesting thing in this post-process is this track embedding. So let me just quickly return here. So we can see that we have some stuff related to memory bank, which is false in our case, so we're not going to read that. And then we call this self.track embedding, which is a query interaction module. So let's find this query interaction module. Again, same file in the bottom of the file, query interaction layer, which returns this query interaction module. And it just has forward method. And I press continue. So again, now we have data, which only takes in the current track instances, but there's 300 of them, which basically incorporate everything we got out of the single frame prediction and performs this time aggregation network to basically have an extra transformer layer on top of these. So first we do this select active tracks. So let's read this function. So first it has this IOU threshold, which basically filter out, first of all, only those objects that actually matched to anything during Hungarian match, and then only filters out those objects that have too small IOU. So if it's not a great match, it's going to have to be filtered out as well. And this is a technique for training. Coming back to the paper, what we basically want is to say that if an object has detected, if the network has detected something that corresponds to the ground truth object, we want to carry that over. But then sometimes, especially in the beginning, even though we actually start with pre-trained ways from deformable data, which should be quite good. Still, they will just provide not very good object detections in the very beginning. And so in this case, instead of trying to carry them over to the next frame and have the next frame rely on that and try to sort of match this bad detection to the new state of the frame, instead we're just saying that we're going to drop that. So we're dropping this prediction if the IU intersection with the actual ground truth is below 0.5. And also we have this basically false negatives, false positives. So we have random drop tracks and add false positive tracks. We will not read into them in detail, but basically what they do is, well, again, in normal circumstances, we expect to detect 2 objects and then carry over those to the next frame. To make training a bit more interesting, we will sometimes drop these track queries to let the network sort of train in the scenario where not all of the track queries are present, and so it will learn to reinitialize the queries if necessary. We'll also add false positives, so we'll add this guy here, again, to make the life more difficult for the model during training, so that it will see that, okay, we seem to be tracking this object here, which does not seem to correspond to anything on the picture, so this one I need to just drop, and to do that, I need to have that in training. I need to have these false positives that make my life harder, so that when I'm performing the same task in production, not knowing the ground truth, I will also be able to deal with those sort of mistakes and noise. So let's just see what the result of that is. So I have my active track instances, which unfortunately yields 0 instances at this point. And then we have this update track embedding. So update track embedding is exactly what is called time aggregation network in the paper. So you can see that it now receives track instances that only correspond to good matches. So instead of 300 queries, here we'll only see like 25 or even less, depending on how many objects are there on the picture and how many we're actually successfully tracking. And what is happening here is basically written out explicitly single transformer layer. So again, we have self-attention, residual normalization, linear layer, dropout, another normalization, and that's pretty much it. And that's what we return. So and self-attention here defined in the init in the build layers function. This is just the vanilla pytorch.nn.multi-head attention. So full pairwise self-attention. And that's it. So this is how this query interaction module works. So coming back to my sequence processing. So I was reading post-process single frame. So I apply this track embedding, which is the time aggregation network or query interaction module that dropped some queries that apply an extra attention layer, and then I just return it. So I want to come back to the screenshot from the paper again and just sort of reiterate what has happened. So first of all, like big thing that I don't like about this model and TrackFormer as well, and the whole series of so-called end-to-end transformer object detections is that they're not actually end-to-end. So what instead is happening here is, let's say we are looking at frame 1. So we've got some detections, but we sort of look up to the ground truth. So we actually got a lot of detections, 300 of them, but knowing the ground truth, knowing that only 2 are actually in the picture, we perform this Hungarian matching to say that this guy matched here, this guy matched here, and then everything else I can just throw away. So obviously, when we'll be doing the actual detections in the wild, we will not have access to ground truth. So everything that is happening here will not happen in exactly the same way. So instead, we'll have to rely entirely on model prediction, because there's no ground truth to speak of. Like the picture in the model is everything that we have. And so, as we'll see a bit later, we'll rely on those class probability predictions, which is why we need them, even though we only deal with one class currently. So it will look at all the 300 model predictions and actually say that, okay, maybe this guy has too low confidence, this guy has too low confidence, and then these guys are just all right. But this is not the same as looking at ground truth. So in reality, you will expect the queries that get carried over from frame to frame here to be of much less quality, simply because we now don't have access to the ground truth. And so the model will behave slightly differently when we actually use it. And the whole training is done using just detection loss. So we do some stuff with matching. So by carrying over these two already detected objects, as we've seen, the Hungarian matching will be performed only on new detections. So these two objects that are being tracked, they will not be participating in the Hungarian matching loss, which means that once the network detected this person, we're not going to basically reinitialize the same track. We're not going to match it with anything else. But there's no loss that will deal with this sort of carrying over. There's no loss that will deal with like some of the objects being dropped because the confidence is too small. This is just basically the heuristic part of the model. And every time there is a heuristic, every time you have something during the training that you do not have during inference, that's a murky part that ideally should not be there. So now let's also take a look at what is called collective average loss in the paper. So by now we have read single frame inference, post-processing, and this is pretty much it. So we repeat the process for every frame. And as part of that post-processing, we've also generated this losses. And here is the overall forward method, the very first one that we've started to read, the upper one for the parent model. And it basically has this loop over all the frames. And then we take out the actual losses dict from self.criterion.lossesdict. So this guy is going to contain losses for all the 5 frames. So for all the 5 frames, we're going to have IOU, mean squared error, or one loss for bounding boxes, and then classification loss. And to see how that is actually used in the training, I'm going to go just read the code of the main.py. So this is the script that we use to copy stuff around to my Jupyter notebook. So you can see here the main iteration for epoch in range epochs, and it applies train function, which is in this case this train one epoch mod. Again, this is quite short, so we actually iterate over data loader, transfer everything to the same device. Here's where we apply the model, and then we call this criterion. And to understand what's going on here, I've actually launched a debugger. So quickly, how to launch debugger when you have your actual launch script, which has a bunch of command line arguments, as well as it's actually calling this torch distributed launch module. So you can actually just erase this and just call main.py directly in case you have only one GPU. And to launch the debugger with that, I just copy all of that to launch.json and just put it in this args option in launch.json in VS Code. And finally, I'm pressing Command Shift P, press select interpreter, and select the same one I've created in my con environment. So these steps will make sure that the Python you launch, all the libraries and so on are all installed. And this is how I got here. So you can see that this criterion is the clip matcher the same one we've seen before that perform the actual Hungarian matching loss. So here is the definition for that one. Remember, when we did the matching, we used this function called match for single frame, and now we're just calling it. So calling this module, just call it this forward function, and you can see that it's rather short, and it's actually just taking the losses that were already computed before, and there's a bunch of them because I'm just going to print them all out. So we have frame 0 loss cross entropy, frame 0 loss bounding box, frame 0 loss GRAU, and so on and so forth for all the frames, and some of them are auxiliary losses. And then what we do is we just get number of examples and actually just divide all the losses by the number of examples. So this is it. And finally, if we return here, let me just continue. So we get this weight dictionary that usually just tells us which losses have which weight. And you can see that all the auxiliary losses are not present here, and we only have cross entropy, bounding boxes, and GIU for all the frames. So then we basically just sum all the losses together. So collective average loss is a fancy way of saying that let's divide the loss by the number of objects, and then take the loss, all the losses for all the intermediate layers, for bounding boxes, for classification, for all the 5 frames, and then just sum them all up. That's the collective average loss. So now let's quickly talk about evaluation. So evaluation calls this eval.py script. We can see that this is the main function. We basically load the data set, load the model, then we iterate over sequences. So these are the names of the sequences from MOT17 dataset. And then we have this detector that is used to detect some objects. And then we call this evaluator that actually computes some metrics. So if we go to detector and detector detect method, it's again rather short. We can see that it has probability threshold, area threshold, and then we iterate over basically all the frames in a sequence. We load it into the image. Then we call this inference sealable image function, which is basically the same as we've seen, just the forward path, just the forward pass of the model. So it will not have access to ground truth. So it just basically gets the predictions out of the model. And then we do this filtering. So filter by score, filter by area. So score is going to compare the score to probability threshold, which was 0.7. And area actually just computes the bounding box area in pixels, basically. So we just basically filter out really small objects because probably there's a lot of false detection for that one. And that's it. So this is how we track the objects. So now, like everything we've got out of that, all the actual predictions cannot rely on Hungarian matching, and instead we just get model predictions and just initialize that as our objects being tracked. So coming back to the paper, so this is now the case when we don't know ground truth. We have 300 predictions from the model, and so we will filter out the ones with too small area, and we'll filter out the ones with low confidence threshold of the model. Everything else will be carried over and will be used for tracking. So this is it for today. Hope you enjoyed it. Hope it was quite useful and insightful. And see you soon.